Hi everyone, welcome to this lecture for AP Environmental Science on geothermal energy. This covers one learning objective, which is topic 6.10, and we're still with the same enduring understanding as all of the previous energy resources, but we need to describe the use of geothermal power and power generation, and describe the effects of geothermal energy and power generation on the environment. So essentially, how is geothermal used, and what are the impacts on the environment, and then a little bit about human health. All right, so what is geothermal energy? Geothermal energy is when we use the heat of the Earth's crust to either heat or cool our structures, our buildings, or we use it to generate electricity. We're going to focus on that electricity generation for pretty much most of this, but we're going to mention geothermal heating and cooling and discuss it as well. But essentially with a power plant, there's a few different ways that you can have a geothermal power plant, and you see two examples over there on the right of kind of an overview. But you're going to have pipes that go underground, and they're going to go and collect hot water, or they're going to send water down in order to be heated, and that water is then going to turn to steam, especially as it changes in pressure differential from underneath the Earth's crust up to the surface. It's going to turn to steam, and it's going to power a turbine, which is going to power a generator, which is going to generate electricity. So we're still with that steam turns a turbine, which powers a generator system. Okay, that steam can then be condensed, it can be cooled, and it can be sent down and recycled, or it can be used for other purposes. Geothermal heating and cooling, you will also see this as passive geothermal sometimes, but passive geothermal is actually a little bit different, but I'll talk about it in a second. Geothermal heating and cooling is essentially where you send down pipes, and you can either have a flowing liquid of water or air that goes through these pipes, and they're not as deep as a geothermal power plant. We're talking like maybe 10, 15, 20 feet deep, and there's a constant steady state of about 50 degrees Celsius when you get, 50 degrees Fahrenheit, 10 degrees Celsius when you get down about 10, 15, 20 feet, depending on the location. Here in the temperate Colorado, you have to go down maybe 10 feet, even less, maybe 5 feet. But if you send pipes down that far, you can push air through it, and that 50-degree air is going to come up and cool a house during summer or warm a house during winter. So back to a geothermal power plant. This diagram is showing a pool of water down below, but please note that it is not a pool of water. It's just groundwater that is hot, and it's in the rock. It's not like a giant cave with water. This can also be a closed circuit where you have these pipes that are totally closed, and the water inside the pipes gets heated. Doesn't really matter. Anyway, you're going to have hot water from way down in the Earth's crust at some place. All right, and that hot water is going to be pumped up to the surface, and it's going to generate steam due to two reasons. One is because it's really hot, and two, because of the pressure differential. It's getting compressed down by all the rock above it when it's in the Earth's crust, and it's compacting down into a liquid. But then if you relieve that pressure, it's going to evaporate into a vapor. So steam. That steam is going to be channeled through a turbine. The kinetic energy of the moving steam is going to power a generator, which generates your electricity. And then that steam is going to be cooled at cooling towers or cooling ponds or a condenser, and be sent back down to the injection well, where it can be go through that entire process again. Right, so geothermal heating and cooling, again, you go more shallow, so you don't go way deep down into the Earth's crust. We're not talking hundreds or thousands of feet, we're talking like tens of feet. So let's look at these greenhouses on the right, because we have different seasons. We have winter and we have summer. So if we have constant 50 degrees Fahrenheit or 10 degrees Celsius in the soil, that's supposed to be Celsius, and the soil, you can send really cold air, like 32 degrees down into that. It's going to warm up, it's going to rise back up. You'll have fans to circulate this, and it'll rise back up at 50 degrees, and it'll keep your greenhouse at 50 degrees Fahrenheit, which is well above freezing, and your plants won't freeze. Meanwhile, in the summer, if your greenhouse is baking under the sun, you can send hot air down there, let's say like 90 degrees, and then that hot air is going to cool and it'll rise back up as 50-degree air so that your greenhouse will be a little bit cooler than it otherwise would, maybe like, I don't know, 60, 70, 75, 80 degrees. Okay. This is typically going to be used at home, residential, or greenhouse, small scale industrial, but typically more so residential or greenhouses is where you typically see this. And then I said I would talk about passive geothermal. Passive geothermal would be basically the same thing as what we saw with the geothermal heating and cooling, except you wouldn't have fans. So it's a little bit more active if you're putting electricity into it to circulate that air with fans, but it'd be passive if it was just passive circulation, if it was just working on a convection current. Anyway, geothermal is renewable. There is a very consistent heat in the Earth's surface, and we're not drawing up enough energy to cool the Earth at all because the molten core of the Earth, the mantle, are going to continue to heat the crust, and the all of the radioactive decay of any radioactive isotope is also going to be warming up the crust. Plus plate tectonics and all of those things continues to warm the crust, and the small little tiny amount of energy that we extract is totally negligible. Okay, it's a very consistent energy supply, so the heat of the Earth's crust doesn't change from summer to winter. It stays at a constant temperature, whether that is deep geothermal at a geothermal power plant or whether it's more shallow at a with geothermal heating and cooling. One thing I should point out on that last slide that you probably noticed in the pictures was that there was steam coming off of those cooling towers. Just know that that is just steam. It is not any type of atmospheric pollutant. There is no atmospheric pollutants created through geothermal, except for a little tiny bit, which we'll talk about in a couple slides. Anyway, so for global distribution, where we find most geothermal is actually in the United States. So if we rank, what I did was go onto Wikipedia and I ranked geothermal by its capacity in megawatts in 2010 because 2020 didn't have as much data. And in terms of the megawatts produced, United States and then the Philippines, Indonesia, you can go down and read this. I should point out that in terms of percent geothermal, Iceland is the leading country with 30% of its nation's electricity produced through geothermal. The Philippines is second with 27%. Okay, and then El Salvador at a very close third with 25%. Now there's reasons for that, and the reason for that is because they are all on plate boundaries with the divergence of the North American and the Eurasian plate for Iceland, as well as the hot spot that is underneath Iceland, with all of the different plates that are down in Southeast Asia, and the Caribbean plate and the North American plate at El Salvador. So geothermal is, you will mostly see it around around where we have tectonic activity, where we have plates converging or diverging, very much less so in the middle of a continent. Now, you guys have probably already read this, but capital costs are pretty high for geothermal. It's mostly the cost of drilling because you do have to go down really far for geothermal energy, and you have about 1/5 of your wells fail. So there's definitely a huge cost associated with geothermal. However, you do have a relatively quick return on that investment, especially once you start producing electricity because your only input is water. Okay, it is very scalable. You can have very small geothermal power plants. You can have very large geothermal power plants. It really just depends on the scale that you're using or that you want. And then it really is a small share of the market, but it is growing. Like I said, with the availability, you typically see it around tectonic plates. So if we look at everything that goes into geothermal, the darker the red, the more suitable it is. lighter shades of red or orange, the less suitable, and then the white on this map is where it is not suitable at all. So it wouldn't be really a good option in the Midwest of the United States. It wouldn't be a good option in the southern United States. Wouldn't be a good option in the Scandinavian countries, but it is an option in many other places around the world. So it's one of those things where a geothermal power plant is really dependent on the location. And just picture the map of tectonic plate boundaries and hotspots, and you're going to essentially get where geothermal can be used. So it is very has great potential for growth in countries like Japan or New Zealand, Indonesia, even China and India, through much of Eastern Europe, and then the Western United States and much of Mexico and Central America, and then the west coast of South America. Now, the good news is that geothermal heating and cooling can be used basically anywhere. You just have to dig down deep enough. The only place that I would say that it really isn't applicable is once you get into the Arctic and you're starting to get permafrost, but that is really more, not many. You can still dig down deep enough. You just have to dig underneath of that permafrost, okay, which can in itself be many meters thick. So geothermal heating and cooling may be not applicable in the Arctic, but pretty much anywhere else it is definitely applicable. So the environmental impact of geothermal is pretty minimal. That steam can carry some minerals and gases. The minerals are typically harmless, but you do have some trace amounts of heavy metals that can be brought up with that steam. Most of that is going to stay in the water once it condenses, and it won't be released out into the atmosphere. There is some geothermal power plants that send their waste heat water or their like the hot water that they condense down into steam or that they condense down from steam into like mineral spas, and it's great, and it's supposed to like actually help your skin. So I would say that it's not really a big deal unless they're pumping it directly into a river or a creek, which with regulations they hopefully should not be doing. The gases that can be released are a little bit of carbon dioxide, a little bit of nitrogen oxides or nitrous oxides. Sulfur dioxide is probably the biggest one, followed by hydrogen sulfide. However, their emission rates are very, very, very low compared to other energy sources. So for example, it's like 0.000045 tons of carbon dioxide per kilowatt hour. We can compare that to coal, which is like 10 orders of magnitude higher. Okay, so it is really negligible amounts of carbon dioxide, sulfur dioxide, etc., but you can release a tiny, tiny, tiny amount. And then boring of the wells and water injection can lead to ground instability and some minor tremors. So you do have to get that water down there, and you do have to go through all of these layers of rock, which can destabilize some of the geology of the area. And then the human health impacts are little to none. Some of the pollutants can escape and cause dizziness and minor respiratory issues. Some trace heavy metals can enter drinking water and aquifers or surface water, but that was all that I can find for the human health effects. It is one of the safest with 0.001 to 0.01 deaths per terawatt hour. And again, some of these minerals may not be good, but some of these minerals can be like used in geothermal hot spring spas. So this is, for example, the Blue Lagoon in Iceland, which is a man-made pool, and it's a geothermal spa where they have a geothermal power plant over here, and then they pump that hot water over to the spa, and the minerals in it are supposed to be good for people's skin. So it's basically like if you were going to any type of hot spring spa, except this is a artificial hot spring spa rather than something that you'd see in like Idaho Springs, for example, or Glenwood Springs. All right, so we talked about how we can use geothermal energy. They focus on electricity production, but you should also know passive heating and cooling, geothermal heating and cooling. I slip and say passive all the time. And then some of the issues with geothermal. So it is not applicable for many places in the world because it can be cost prohibitive, especially in developing countries. And it is generally found only generally applicable only on plate boundaries. It can also release small amounts of hydrogen sulfide, sulfur dioxide, and other atmospheric pollutants, but again, minimal compared to some of the other energy sources. Hydrogen sulfide is kind of unique to geothermal. None of our other energy sources release hydrogen sulfide, but again, probably minor amounts or usually minor amounts.